I'm aware that we've got some material I'd like to cover before tomorrow. My fear is that if we don't push on a little bit, we won't actually cover Gaussian processes in the Gaussian process summer school. So that might not be good. So what I thought I'd do now is just go quickly through some of the things we've been doing, and I've got more results in the slides, but just to show you how you do a sort of one of the examples of the model fit. So it's actually written a slightly different way in the, of course, and there's many ways you can do it, but what I'm doing here is I'm creating the matrix phi from the training data. So I've just picked up where yesterday's lab left off. So X is the Olympic years. And I'm using H stack, which I think in my mind means horizontal stack. And I'm building a vector of 1s, which is the shape of X. Then I have X and then X squared. And that's giving me my training data in the matrix phi. That's the design matrix phi. So I use a capital P because it's a matrix. And that's a little convention I use whenever I'm doing programming in maths. If it was a vector, I'd use a small p. I can't, normally I do vectors bold, but you can't do that in code. So there's me creating phi. Now, this is solving the system phi transpose phi. This is multiplying phi transpose times phi, np dot dot. Remember what we wanted was W was equal to the inverse of this times phi transpose y. But we weren't going to do that by inverting phi transpose phi. The correct way to do it is solving this linear algebra system. So if we, for example, put linalg.solve, which is I think something that is in the lab sheet too, it comes up in the help here. Solve a linear equation or system of linear scaled equations, computes the exact solution X of the well-determined rank linear matrix equation AX equals B. That's how they like to write it, the numerical analysis people. So A is a matrix, it's our phi transpose phi, and that's the first argument. And then B is this vector, phi transpose y, and the X is our W. So we're getting W out. W is equal, solve that linear system of equations. I'm going to get rid of that bit. How do I get rid of that? Oh, I don't know. Oh, I don't know. Okay, we'll just have to leave it there. I managed it earlier. So now, that's given me the solution. So let's have a little look at just what this solution is. So it's solution, the coefficient, the bias is about 600. The linear coefficient is a negative, a small negative thing like we had before. It's about 0.6. And then there's a slight quadratic coefficient of 1.6 times 10 to the minus 4. Why is that small? Well, it's having to multiply 1980 squared. So in order for those results to come out around 4, it's having to multiply a small number by a squared thing. So although it's a small coefficient, we actually see when, okay, next step is to create this test data. So I'm creating a vector of test. Now this little trick here, this is a Python trick to take that vector and turn it into a matrix which has the data points on the rows. So it's a design matrix. So this is a little, I don't want to go into the details of how that works, but that's a little Python trick for doing that. And then I'm making the test data. So this is so I can do the plot, yeah? So I'm asking, I want to see the response of the function at 130 points between 1890 and 2020. We're going to predict what Stephen's going to do in the 2016 Olympics, what time he's going to have to run. And so and then I'm creating phi again, yeah? So the same thing but with X test. So now I just need to multiply this matrix of phi, the test phi, by W. And the matrix multiply is giving me W1 times the bias plus W2 times the linear, sorry, W0 times the bias plus W1 times the linear plus W2 times the quadratic term. And then I can plot that and there's my result, yeah? So it's a quadratic fit to the data and it says that Stephen will have to run slower. So again, it's not realistic. I mean, it's stupid, isn't it? It would actually say that if you went over here in 100 years' time, it would say that people are going to get running slower. So that's the consequence of not including the right sort of basis in the data. Okay, so we'll go back to, I mean, the slides sort of pick up there. So, of course, we've already asked about, how do I get rid of that? I need to move away from full screen. Exit full screen, look at that. When I said that, the computer understood and it told me how to do it. Okay, good. My computer is artificially sentient. I didn't want that one, but I do want this one. Let's hope that comes up in the right place. Okay. So then we can also solve for sigma squared, which we didn't do in that session. So some reading there, the matrix and vector reviewer, if that's something you're not familiar with, then you can read in Rogers and Girolami. And that matrix reference manual of Mike Brooks is just an excellent resource. It's freely available online. So, here's some different polynomial fits. So what we can do is we can sort of see what happens as we increase the order of that polynomial basis. So I showed you there, or in the lab we've done a quadratic basis, but this is a 0th order basis, just an offset, right? And we can see that doesn't do very well. That says the speed is constant and it just selects the average speed. There's the linear fit. There's the quadratic one that we've just done in the lab, but we can now go cubic. Well, that looks nicer, because look at it, it's sort of following better, yeah? Or we can go quartic. That's nicer as well. Or we can go quintic. Whoa, what's going on here? Oh, now we get a better fit, we get a tighter fit to the data at each time. The error is actually dropping, the variant, the error is minus 32. So it's going down. It goes down as we get each case. The error goes down, yeah? Every time we increase the basis, the error improves in terms of we get a better fit to our existing data. But do we genuinely believe the best fit here? Is it really going to be the case that the time goes flying off in that way? This is a major problem with the polynomial basis. And it comes about because what going on inside this code was actually reasonably difficult to write, because it's computing 2012 to the power of 6. And then it's trying to work out a coefficient. The size of that coefficient is then of order computer precision. These bases are terrible for working with because of things like that. If we were to use the RBF basis, then the result of the basis would always be between 0 and 1. Much better regularized for the computer. There can also be numerical problems there. So what happens with these polynomial bases is they come and do these crazy things. They sort of make these wild predictions. And a small change in any of these data points could flip that prediction from going down to going all the way up. So they're often not very stable in their predictions. So how do we sort of propose, how do we check what's going to happen? How do we understand when this is a problem? Well, so what we do is we tend to keep out a test data set. So that was the training data we've looked at. And here's a sensible way of doing a test data set. In this example, because we know we're trying to predict into the future, what we might want to do is predict the trend from the historical data up to, I think that's 1980 there, and then try and predict what is going on from 1980 onwards. So in this case, we build the model with the training data up to 1980, and then we test. We have a validation error, what the error is for these future points. So here, I'm doing the same thing. So what was going on in this plot is I'm plotting the error as we increase the order of the polynomial, the error just goes down. In fact, as we get to a 17th order polynomial, it would go to 0. The polynomial would be able to interpolate every data point if we got the numerics right. They're quite difficult to get right. I know, I've tried it. But what we really want to do is get the performance on these test data. So now I'm doing the same thing, and what we see is this effect, right? As we change the order of the polynomial, look, it's flipping around all over the place. And it turns out that the best error actually was for this second order model. So this 1. Yeah? Still, it's not very good. But that's the best error. Now, we're going to try and deal with that and improve things. And we're going to improve things by not using a point estimate of the regression model. And we'll see we actually get much better. So here's a little problem, is what would happen if we moved one of these points just a little bit, not the quadratic one, but these fits would actually change a lot. Look at that, between the order of the fit there, changing the fit by 1 order, and the predictions are going in completely opposite direction. It's nice to use polynomials because this effect is exaggerated for polynomials. It's crazy. But actually, this effect would also happen if I moved one of these data points just a little bit. It would also happen if I moved the coefficient just a little bit. Because this is something like, take the coefficient associated with the 6th order polynomial, move it just a little bit in one way, and you just get an enormous effect. So you want to know the sensitivity of these coefficients. You want to know, have a distribution over them, and perhaps if you can average over all the possible solutions that are sensible, you may get a better prediction. And indeed, we'll show that you do that. And that's the so-called Bayesian approach. I don't like the word Bayesian because it makes it sound like it's a religion. It's not a religion. It's just the right thing to do. So the old word for it was called inverse probability. But I'm going to try and justify that when it comes up. But we'll leave that for the moment, and I'll just show you, just while we're on the subject. So we've been predicting, trying to extrapolate into the future. If this was malaria incident across north-south of Uganda, we may not want to predict into the future. And a really useful model checking technique would be to do the so-called leave one out error. And we're going to see some of the interesting effects that you get of stability of these solutions here. So there's a point in green, and what I'm going to do is this fit for each polynomial will be the fit with that green point removed. And we're going to try removing every green point. Yeah? So we do it for the 0th order, and obviously it's a very stable solution. It's low variance solution. Doesn't move very much. And then we average the error that we get in trying to predict. So we're now training on all points but 1. We get an error. We do that. So I think, I can't remember, it's 17 points. Let's say it's 17. So we train on 16, test on 1. We do that 17 times. And we get an error for that 1 point 17 times. And this is called the leave one out error. And that's what I'm plotting now. So there it is for the 0th order model. For the linear model, again, I mean, look, when we leave this one out, because it's an outlier, it changes the most, yeah? So it's actually pretty stable for all these, but when you leave that one out, it moves a lot because that one has a big effect. Same thing, the leave one out error is minus 0.15413. So it's actually better, as you might hope. Here's the quadratic, same thing again. See how the curve's moving as I leave it out? These are all the different fits. It's actually worse. So it turns out that under this criterion, the quadratic is also best. But this criterion, what's it testing for? It's testing for interpolation between the points. It's testing our ability to predict what would have happened if there'd been an Olympics in 1982. Yeah? Now notice what's going on now as we increase the order of the polynomial. We're going to start getting much larger fluctuations, particularly I think as we move Stephen there at the end, that makes quite a big difference as we remove and we try and predict across him. So the errors get much worse. So that's the leave one out cross-validation error, and that's a nice technique for trying to assess the quality of your model. So this is part answer to Ernest's question from before about what basis should I choose. Well, you can cross-validate to try and see which of these things is better. Yeah, this is the standard model checking technique. It's always useful. But that's very slow because you basically have to build your model n times, where n is the number of data, because you have to build the model on all the rest of the data. So another thing we use is something called X-fold cross-validation, where what you do is you leave out, so in 5-fold cross-validation you leave out a fifth of your data. It won't be exactly a fifth, and you do the fit 5 times. So you do the same thing, but now you leave out, here it's 5 points, there it's 1, 2, 3, 4, 5 points, there it's 1, 2, 3, 4, 5, 6 points, there it's 1, 2, 3, 4, 5 points, and there it's 1, 2, 3, 4, 5 points. So there must be 21 points in this data set. no, 26 points or something, whatever. So, and then you just do the testing for all those 5 different cases, yeah? So this is another approach to doing the model validation where you only need to fit the model 5 times. Now it's slightly worse than the leave one out cross validation in terms of an estimate of the error, because of course you're only fitting your model on 80% of your data at any one time. When you're trying to predict the quality of what you're doing, you're only using 80% of your data to predict the quality. So you might not get as good an estimate of the best model to choose. And indeed, we are actually going now wasn't that different from before? So with the 5-fold cross-validation, we're picking the minimum error is the linear model. And was that the same for the, I can't remember now. Yeah, no, linear model again. But we see a slightly different curve. You know, it's a little bit noisier. This is a little bit less stable as an estimate of the generalization error. So that's how we're trying to do the generalization. So that's model checking within the context of these model fits. I'm going to move on to underdetermined systems now, so I just want to stop there and check if there are questions about that, cross-validation and validation. So, I mean, to be honest, I think the validation thing was the right thing to do here if we're trying to predict in the future. It depends which question you're asking. If you're trying to build a model that is trying to predict in the future, validation was the right thing. That selected the quadratic. If we're trying to interpolate between the different years, cross-validation was the correct thing to do. They tested slightly different things. You can't really do cross-validation for the extrapolation into the future because there's only one point. You know, you can only basically sort of take some portion of your data and say stop and then predict into the future. But for this interpolation, you can do this cross-validation approach. Very, very commonly used for model checking and very commonly quoted on a given data set for a particular fit. Questions about that?
For the validation that uses polynomial 0 order, the stability, does that mean anything? Can you make a sort of a variation of how points are offset to that particular?
It is, there is, you know, I'm non-expert on this, but it does mean something. And there's an analysis of this generalization that is called Bias-variance analysis. And you can see it going on exactly here. There are different types of error that these models are making. And I mean, I never get involved in this type of decomposition because it's not my domain, but it's a useful decomposition. The type of error that this model making is known as variance. It's got the capability to fit the data, but it's overfitting. It's over-interpolating. Yeah? So the error goes high because it sort of wiggles around too much between the data. And there's this paper by Gieman and Gieman, very elegant, that takes the error and decomposes it into these 2 components. There is error due to variance, which is this case, and that will be very unstable. The fits will be unstable according to how you change the data, or error due to bias, which is this case. The model is not capable of responding to your data. I think that this is a model mismatch problem. I mean, when I view it very differently because I take the probabilistic approach. So this is due to model misspecification and over-reliance on your noise model, you know, to take account of what's going on in your data. Basically, this says marathons are all run at 3.5 minutes per kilometer with variance, well, which has a standard deviation of about half a minute. Absolutely not right. Clearly wrong. So it's a model misspecification. These models are much more powerful. In the non-Bayesian world, the idea is that they're overfitting. They're more powerful, but they're not regularized. So they tend to over-interpolate, and that's known as variance error. And these will tend to be less stable. That's a nice example of how the cross-validation fit is suddenly changing. Look at that. That's the same model order, but different variant of the data set. And the prediction in the future, whoop. So that's high variance on the predictions. That's brilliant, that one. That's a nice example to stop on, yeah. So that type of error that's coming from, I mean, it's a largish variation than the test set, but you do not want your test set to vary in that way and cause that type of error. That's what we're going to solve with Bayesian approaches in a moment. There was another question, Edith.
My question was about how the method of differentiating between cross-validation and validation.
Yeah.
Actually, you say 10% or something?
Yeah, it's very, yeah. How much you decide to pull out and stuff. I mean, that's part of the. It would be according to the specific problem you're given, and how much. If you've got an enormous amount of data, then actually validation's fine. If you've got loads of data, then you've got no worries. The problems tend to come in this type of situation where you've got 27 data points. But having said that, of course, you can then move to leave one out cross-validation, which is a better estimate. So how much to put in your validation set? I don't know. I don't think that there's a right answer, but obviously, I mean, you often see people using like 20%. John, how much would you put in a validation set?
Like as much as we can process easily?
Yeah.
Depends how fast it is.
Yeah, that's another. So yeah, sometimes they're practical. Yeah, I'll train on. Yeah, so someone might give you 25 million data points, and then you might say, well, I'm going to train on the first 500,000, and I'm going to validate on the 24.5 million. And you're doing that because your algorithm can only work on 500,000 data points. So it varies. But in small data is a really interesting area. I mean, we're in the era of big data, but small data is a really interesting area. And actually, when the worlds collide, so that's where we're getting to nowadays. I like small data, difficult, challenging problems. Big data brings lots of engineering problems, but very often the sort of things people do with big data, the model is very well determined because of the large amount of data. But the most interesting area is when big data is small. So when we're trying to analyze a very, very complex system, like the human cell, you could get all the gene expression data in the world about a cell. And the system is so complicated that you're in the small data regime in terms of the complexity of what your model needs to be to model the human cell, but you have big data. You've got terabytes of data, but it's not enough to determine the complexity of your system. And that's the fascinating future that faces us, I think. So that's where you get all the challenges of small data and the engineering challenges of big data. And I think that's where it's at. You want to make complex inferences from massive data. And I really think that's the most exciting thing happening in machine learning at the moment. Okay, so other questions? So, underdetermined systems. I'm a great believer in those high variance models. I think that I never want to have my model well determined, and I'll try and persuade you. This is my sort of philosophy. And what I'm going to use to illustrate this system, so I want a complex model because I want it to be able to represent complex inference and complex things. I want to have a model that is close to the model of that cell. But I know when I fit it, I'll get these high variance responses that the model will make confident, crazy predictions. So how am I going to deal with it? Well, let's look at one data point. How are we going to, and let's go back to linear regression. How are we going to do linear regression with one data point, right? This is an underdetermined system. We have two unknowns, M and C, and we have one observation. Oh dear. We can't determine what this parameter is. How do we deal with the overdetermined system? What do we need to introduce? Anyone? Sorry? Some noise. Yeah. But I even like to think of that as a latent variable. We introduced an additional unobserved component plus epsilon. Yeah? And we said we're going to assume that was drawn from a probability distribution. And I think that's my preferred way of looking at noise. We modeled what was unmodeled. We modeled the unmodeled. But this is now a problem in our own model. Now here's a proposed solution. So I want to know these two parameters, but what if we do the same thing again? So what I'm going to do is I'm going to say, well, we can compute M if we know C and this data point. Yeah? So this is just reordering the linear equation to say, well, if I know C, I can give you a value for M. So what do you think I'm now going to do with C?
To estimate C.
Pardon?
To estimate C.
To estimate C, but I can't estimate C because I can't estimate M and C simultaneously. What I'm saying is, if I'm given C, I can estimate M. If I'm given C and X and Y, that should be X1 on the bottom. If I'm given Y1, X1 and C, I can estimate M. So what am I going to do with C? It's too quiet, I can't hear. I have to assume something. What should I assume? What did I assume for the noise? I could assume it's a constant, but that would keep things fixed.
You assume it is 0.
I could assume it's 0. So if I assume C was 0, then I would basically be observing a data point at 0, 0. That would be implicitly what I would be doing, yeah? Why don't I take C as a random number, Ibrahim? You have just reinvented inverse probability. Clearly the sensible thing to do. Clearly. If before, the bit that I didn't know was the world model, that the difference between me and the world, I treated that as a random number, the bit I don't know now, C, let me treat that as a random number. So here's an example of the fit if C is 1.8. Here's an example of the fit if C is minus 0.077. Here's an example if it's minus 4.01. So on. Here's a bunch of examples. If we assume C is drawn from a Gaussian distribution with variance 4, standard deviation 2, that's the family of solutions we get. Now, I love that family of solutions because that is not just telling me where my data point is. It's telling me with a distribution where I'm going to be either side. I love that model. I mean, there's an issue here because if there's noise, we should also have a bit of uncertainty. We've ignored any noise. We're just looking at the underdetermined system here. But this is a beautiful model of data. I mean, marginally, it's a beautiful model of data. If you give me one data point and I fit this model without prior of C, then basically what I'm saying is, yeah, as we start approaching 1, you're probably going to get closer to that data point. And as we move away, you're going to get further away. And in the far distant regime, I have no idea what's going to happen. I love underdetermined systems. In fact, I do not want to fit a linear model if I've observed 2 data points, because all this beautiful uncertainty immediately disappears. So I love the underdetermined. This is actually very closely related to the high variance situation. But if I had 2 data points, basically it would go, it goes right through there. Yeah? And then the predictions would be super confident down there. If all we had was Stephen Kiptrich's time in 2012, and then we were trying to make predictions from that, that would be a great model. Chances are in the future it's going to be quite similar to that, but since we know nothing about what's going on or what this race was or anything else, it could be anywhere either side. Our best guess is roughly centered around here. Actually, it will be centered a little bit up because the prior says it's equally distributed around this region. So if you look at typically there's more belief in it being high after the fact and low before the fact because the prior pulls things down towards, I've specifically chosen a bad prior actually because, well, it's a bad prior, I don't know if it's a bad prior, but I've chosen a prior that pulls the intercept down to here. So what we want to do is we want to sustain that family of solutions. So this is implicitly a family. This isn't quite Bayesian inference because I'm not sustaining uncertainty over M quite properly here. What I'm just doing is explicitly saying, well, if we put a probability distribution over C, we sort of get a probability distribution over the solutions. And I think that's a beautiful concept. So Bayesian inference, or inverse probability, says we're not going to look for a single point solution. We're going to look at all the family of solutions that are consistent with our data and consistent with our prior. And that's sort of what we're visualizing approximately there. Not quite true, but I think it's a nice way to introduce So to deal with overdetermined, we introduce a probability distribution for the noise, and to deal with underdetermined, we introduce a probability distribution for the parameter. So what are we doing is, what I said at the beginning is that we had a deterministic model of the world, and then we had a stochastic model of the difference between what we believed and the world. And now we're moving to a zone where we have a stochastic model for both things. And that is a wonderful place to be. That's when everything gets interesting, because that's when you express the uncertainty about your own model that's vital. If we are thinking of, if we genuinely could write down a complex model of how a cell interacts with all the right uncertainties over all the parts of the cell, what we would want to do is combine that with data and see where we were getting confidence about how the cell was working. Yeah? We would want to say, oh, that data told us how this component worked. It would be a wonderful thing. Now, it's too complex to do that. But if you could do that, that would be, to me, the true expression of how science should work. You have a distribution over the way you think the world's working. You combine that with data, and then you get an updated picture on the way the cell works. And this is exactly what Laplace did when he fitted things to data in the sky. They used these motivations. In fact, there's something called the Laplace approximation that Laplace invented for doing this process. And he even invented the Gaussian distribution, which is odd why it's called Gaussian. He invented the Gaussian distribution to perform this process using the Laplace approximation, which is something we use to this day in Gaussian processes in order to do this approach. So this is known as a Bayesian treatment. I think that name's terrible for many reasons. Bayes did not propose this. The reason Bayes is associated with it is because he wrote down a probability distribution for a set of parameters. And Fisher coined this term to make fun of this treatment, which I think is absurd. Fisher did some great work, but what he really did there set back data analysis for years, I believe. So there's various reading about the Bayesian treatment there. But let's look at what Bayesian regression means. So what this requires us to do is not just specify a model in terms of a functional relationship. It requires us to also specify a belief over our parameters before we start. So it requires us to say, well, we think that this intercept is some variance, zero mean with some variance. We don't know what it is, but we believe it's going to be some value. Now, there's a lot of controversy about setting priors over these parameters, and people claim, oh, that's a really bad thing, or where does the prior come from? Well, where does the model come from? The prior is part of the model. One must always see this as part of your modeling. It will always be wrong, but it's integrated, and Gaussian processes really show that. These two become one and the same. The prior incorporates your world assumptions. The prior needs to incorporate smoothness if you believe in smoothness. If you believe in linearity, the prior needs to incorporate linearity. In this case, it's a prior over what we thought, what we believe runners were most likely to run the marathon in the year of Christ's birth. That's the interpretation of it in this case, yeah? So sometimes they have real interpretations, and you can say, they probably ran it in about 5 minutes a kilometer, or whatever, right? You can put whatever you like. But that's what it's actually saying in this case. It's got physical meaning for the marathon example. So what you need to do is you combine this prior. So here I've written down the prior, and I've actually used not sure what variance I've used here. I've clearly not used a variance of 4, because then I would have standard deviations around 2. I'm suggesting I would have used a variance of 0.25 or something. It looks like, well, maybe, I think even smaller, because look, this is more than 2 standard deviations to 1. So I've got some smallish variance on this value for C. What you do in Bayesian inference is you need to combine the prior with your likelihood. Why do you do this? I'm not sure my slides are very good on this. I'll probably write something on the board in a moment. This is the likelihood of a data point, yeah? So what we can do, so I'll take a little step back here. What I'm showing here is the prior distribution as a function of C, yeah? What I want to do is I want to take C, and I want to find out what I believe about C after I've observed the data. And the relationship between C beforehand and C afterwards is given by the likelihood. The likelihood is a distribution in Y. It's not a distribution in C. It's a distribution in Y So we can write it as a probability of y given C. Yeah? It's not a probability distribution in C, but it's conditioned on C. C is actually providing the mean of this entire thing, because it's like a minus C in that probability distribution, because we had a y minus mx minus C. So actually, if you look at it here, if you squint for a moment, that's a quadratic in C just as it's a quadratic in y. That happens to be true for Gaussians. If we were putting a prior over sigma squared, that wouldn't be true at all, but it is true here. So it looks Gaussian in C, but it's not a probability distribution in general. It's exceptional here that it sort of is. Well, that's sort of secret. Pretend you ignore that. It's generally not a distribution in C. It's conditioned on C. If we ignored that, C would just be the mean of this Gaussian, yeah? So we've got a P of y given C, and we've got a prior over C. If we multiply those two together, we get the joint distribution of P of y comma C. But what we want to know is the posterior distribution. Well, we want to know two things. We want to know the posterior distribution, which is the probability of C given y. So instead of estimating C directly, we're going to come up with a distribution over C that is influenced by our prior and our likelihood. Yeah? Now, because this is just the product rule of probability, this is the easiest theorem to prove in the world. I mean, theorem is not even a sensible word for it. What I want is P of C given y, the distribution for the parameter of interest given my observation. So the product rule says P of y given C times P of C is equal to P of y comma C. The joint distribution of y and C is equal to the product of the conditional of y given C and the marginal distribution of C. So what do I need to put down here to also get P of y comma C? P of y. Precisely. And that's another important quantity in Bayesian inference. P of y. That means I can now relate the posterior. So this one here is called the posterior. It's not because of bottoms. It's because it's what you observe after you've seen the data. Yeah? So a posteriori is Italian for afterwards. Now, you would think that that would mean that what you observed before the data is therefore the anterior. I think it should be called the anterior, but we don't say that, we say the prior, because in, I guess it's a priori is the Italian, so this becomes the prior. So this is before we see the data, the prior distribution. And this here is the likelihood. It's what we've been working with already. And then this term, this has many names. My favorite name is marginal likelihood. Why marginal likelihood? Because it's like the likelihood of the data with that parameter marginalized. And why marginalized? What does marginalization mean? Well, to get that likelihood, you need to use the sum rule. So these are the two rules of probability. It's such a gorgeous subject because there's only these two rules. So marginalization. So in the continuous case, that's integration. P of y is equal to P of y comma C integrated over C. Why is that marginalization a good term? It's because the result of that is C has disappeared from your expression. Yeah? So it's not there in your model. So you can think of it as having been written in the margin of the paper. Oh, there was a thing here, C, and it's now in the margin of the paper. So marginalization means taking the parameter out of the model, getting a marginal likelihood, which is just the likelihood of that model with that parameter now in the margin. Yeah? And this is the main object. This is the thing you want to maximize the likelihood of now. Maximum marginal likelihood, sometimes called type 2 likelihood or empirical Bayes. You then go and look at the marginal likelihood of that. That's one of the strategies you can do. So you get this relationship. Now pictorially, what does that look like? So this is the prior, it's a distribution over C. The likelihood is a function of C because it's got C in the mean here. So we can express it as a function of C. And because the Gaussians the way they are, it looks like a Gaussian. it does look like a Gaussian, and it will be correctly normalized, but it's not, in general, a proper probability distribution. So the process you're doing here, in order to relate, to get the posterior, what we want from the posterior is this posterior, so let's just finalize what Bayes' rules is, given those product and sum rules, well, just the product rule is all we need, is the posterior, P of C given Y is equal to P of Y given C, the likelihood, times the prior, divided by the marginal likelihood. Now, because this is a probability distribution, as far as C is concerned, that's just a number. It's not a function of C. So another way you can write this, and this is a really useful fact, is you can say, well, that's just proportional to that. As a function of C, this is proportional to that, yeah? The normalizer to give me the, I mean, that's all I need to know because that's a probability distribution. So I can always work out the scale of this by forcing it to be a probability distribution. So the process is, to get the posterior, is multiplication of your prior by your likelihood followed by renormalization of your distribution. Otherwise it's not a probability distribution. So the P of Y scaling is just a renormalization. So pictorially, what's going on here is an argument between the prior and the likelihood about where the data should be, or where the data is, sorry, where the parameter C should be. So these two objects are having a discussion. The prior says, I believe that C should be in this regime here. And then the likelihood says, I have seen the data point, and my data point says to me that C should be in this regime here. And so how do they resolve the argument? They find the common ground, which is between the two. They multiply each other together, and they end up with something that also looks like a Gaussian. Why does it look like a Gaussian? Well, lovely property of Gaussians. We have two objects that are both exponential quadratic C's, yeah? So they're of this form. They have coefficients and maybe some B in here, but they're of an exponential quadratic form. So when I multiply two of those objects together, I basically get the sum of two quadratics in the exponent, and the sum of two quadratics is a quadratic. So the multiplication of these two necessarily leads to a Gaussian. This is very special for Gaussians. You do Bayesian inference with other distributions, all sorts of nasty stuff happens. But these two are very agreeable. They find their common ground where they believe C should be. One from the data, one from the model or the prior. I mean, they're both from the model because the likelihood includes components of the model. And then we get the posterior. The posterior says, yeah, in between these two. Look how closely it's defined on the left-hand side by the blue coming down, by the right-hand side by the red coming down, and it's narrower than the prior, and it's higher peaked, and you've got an updated belief about where C is. Yeah? Any questions on that? This is some involved maths to get the posterior, but it's actually completion of the square of the two quadratics you get. You have to reform it into a new quadratic, so it's just completing the square on that quadratic and then identifying in that square which part must be the mean, which part must be the variance. So that's the system there. But you know, the maths is one thing, but what's actually going on in terms of the domain, the space of the parameters, is this discussion between the prior and the likelihood about what valid parameters can possibly be. Some information is coming from you, the modeler, about what is a valid regime for the parameters, and some information is coming through the likelihood from the data. Of course, you also specified the likelihood, so it's all coming from the modeler in some sense, but it's being influenced by the data. So, multiply likelihood by prior. I like to call the functional forms these exponentiated quadratics because that's what they are, and it avoids the confusion. Gaussians appear all the time, and so the normalized exponentiated quadratic is then a Gaussian. So you do the multiplication, and then you need to renormalize. If we just did the multiplication, obviously it would be much lower than this, because here is 1, right? So they're intersecting at around 1, so its height would be 1, approximately. It would be just like this. And it's been renormalized to ensure its area under the curve is 1, so it's a valid probability probability distribution, one of those things. And the normalization is given by the marginal likelihood, the new normalization, which just turns out to be an important parameter. But we're going to do more on the marginal likelihood tomorrow. So, because of, in this, the functional forms we've chosen, the models we've chosen, we get the product of the likelihood and the prior leads us to something that's also quadratic. So the posterior is also quadratic, and it's a Gaussian. And what we then do, so in theory we have to do this integration to do the marginalization. What we actually do is we just reorder these things to give this the Gaussian form. We complete the square, and then once we've completed the square, we can see what type of Gaussian it is, and that gives us the posterior mean and covariance. Now, for general Bayesian inference, we need multivariate priors, and I use a univariate prior so far. So what I briefly want to do now is just go through how you get multivariate Gaussian densities. We're sort of out of time because it's 12:30, but I just want to get this. Ooh, well, we'll see how we go. I'll just do this bit first. So we want a prior over all our parameters W. So we need a multivariate Gaussian density. Now they're quite easy to generate. So if we have two things like height and weight, and we've got a Gaussian prior over what people's height and weight is, that's a reasonable thing to have perhaps. So here's average height of 1.7 meters, and there's the variance, and here's average weight of 75 kilos and variance of 6 kilos. Standard deviation of 6 kilos. So we can sample from distributions over height and weight, and we can plot them in a two-dimensional space. And what I'm showing here is one contour of the Gaussian density. Yeah? So I'm sampling separately from these two distributions, which is what I just did when I sampled in Python earlier, and just plotting one against the other. Now, that is the independence assumption of probability. It's assuming that I can sample height, and weight is unrelated to height, so that instead of the decomposition we had here, the product rule, it basically says that. So it says that there is no dependence of y on c, that when you integrate, when you marginalize out c, you get no effect on y. So these two things are independent, is what that's saying. But in reality, of course, they're dependent on body mass index. So a better model would be one like this, a joint distribution. So here, now, marginally, these two things are the same. And when you look at this plot, you have to think, so this is like a mountain. It's a Gaussian bump that's twisted. And we're going to get, if you're higher in height, you're more likely to be higher in weight. There's a correlation in this Gaussian. But you can think marginally when you're looking at this beast here, what you see is a hill that looks like this. That's the marginal distribution. Gaussians are very easy to think about because marginally that's all you're doing. You're just looking at the hill from the side, normalizing it to make sure it's the right volume underneath, and marginally we're getting exactly the same marginal distributions as we saw before. But we've now got a correlation. So now I can't just independently sample H from W. What I need to do when I've sampled the H, I have to conditionally sample W. So that is a conditional sample on W given H. And we're going to do a little bit more on what pictorially the conditional distributions are like. But what it means I'm having to do is I sample H. H turns out to be here. My distribution for W is now given by the slice through that mountain. So this mountain is twisted, so actually the mean is up here. It's distributed like this. So I have to slice through that mountain, and my conditional distribution for W now changes. Now, if you think about that operation in the independent example before, this was untwisted. So I sample from here, I get a value here. If I look at the conditional distribution, it's still the view of this density from the side. It doesn't change anything. Okay, it seems like it gets smaller, but that's handled by the renormalization. If I slice through, I always get the same distribution once I've renormalized. So basically, regardless of input here, output there is the same. With this twist on the Gaussian, that doesn't happen. So if I keep doing it, I start to get samples that are aligned more with the axes. Okay, they weren't very nice examples, but they are typically more aligned along this direction. There's a correlation. And people look for correlations in their data, and they're looking for correlation coefficients, etc. So what I just want to show you is what operation that involves. So independent Gaussian densities, distributions over W and distributions over H, that's the joint density. Yeah? So I can easily write down what that joint density is. Just as before, it's just the sum of the quadratics. Yeah, and I've kept the factor of half out. I've got different variances for each distribution and different means. So what I want to do is write that in vector form, because that's how I want to take account of multivariate things. And I can write this form here in this vector form as follows. So I've got a matrix, a vector WH, which is now the thing I'm modeling, and a mean mu1, mu2, and I've got a diagonal matrix here, which is inverted. Yeah? So this is giving me, that's basically just two independent Gaussians multiplied together. I get this diagonal covariance, and I get a vector of means. Now the operation you want to perform, so that's it in matrix form, we can form a correlated Gaussian by just rotating. So what we've done here is we've defined a Gaussian that's so-called axis aligned. All the interesting things about Gaussians occur in the covariance matrices. So this is an uninteresting covariance matrix in some sense, because it's just saying standard deviation sigma 1, standard deviation sigma 2. It looks like that from above, this sausage. But if I rotate it, interesting things start to occur. The conditional distributions get interesting. So the rotated one is like that. Now, it's just rotating these axes. So if we apply that operation to the data, so we rotate the data space, we need to rotate the mean and we need to rotate y. So there's rotating the mean and rotating y. Now I'm going to pull that rotation outside. So this is a rotation matrix. That means it's an orthogonal matrix. Pull that outside the brackets. I now have something of this form, where the covariance matrix, the inverse covariance matrix, I should say, is given by the rotation of the original basis. So what does that rotated basis look like? You can think of those, these are sigma and sigma, right. So physically, this is what's going on with Gaussians. This is sigma 1 and sigma 2. It's a basis, it's an orthonormal basis, which is all on this diagonal matrix. And if I decompose, so I've got a sigma 1, sigma 2, 0, 0. So this is giving me coordinates of that, followed by coordinates of that. Yeah? And I'm rotating that to give me sigma, well, let's put them in the right place. Sigma 2 pointing up and sigma 1 pointing up there. You agree about that rotation? Yeah? Now if I square that, so, or, I mean, I'm squaring the inverse of it, but to invert this, you just put a -1 there, a -1 there, and do the same trick as I did before of flipping the square beforehand. R transpose, I get this thing here, the covariance matrix. So this is like the standard deviations, yeah? These were the standard deviations, they've been rotated, and the covariance matrix is just taking that thing and squaring it, just like the variance is the square. So we're just taking a basis to give us our multidimensional specification of the Gaussian, and we're rotating it around. So embedded in the covariance is a rotation and a scaling on your data, yeah? And this matrix is sort of complicated and stuff, but if you think of it as this rotation and scaling, then actually it helps a lot, I think, with a lot of Gaussian manipulation. This term here, that's the determinant of D. The determinant of D is, I mean, this is such a lovely interpretation of what's going on in a Gaussian, I believe. So the determinant is given by the product of the diagonals of the eigenvalues of a matrix. So the determinant of a diagonal matrix is just the product of the diagonal elements. So that's why at this stage we can write down the determinant. But the determinant itself is actually a measure of volume. So once we've got the determinant of D, because these are like eigenvectors on that basis, the determinant of D is just the same as the determinant of C. Determinants physically are the product of the diagonal elements of the orthogonalized matrix, yeah? So this one is θ1 times θ2. It's that square. It's giving me the volume of the Gaussian. It's the normalization. It's giving me the footprint of that Gaussian. In 3 dimensions, it gives me a cube, yeah? In 4 dimensions, it gives me a hypercube. So it's the normalizer. It's saying the volume of this thing here is given by this value here, and I need to divide that in order to make the integral 1. But it's very much a volume. Now, volumes do not change when you rotate them. And neither do determinants. It's just the rotated volume. Yeah? So it's got this real physical meaning, the determinant. It's the space over which the Gaussian is sitting. And that's important too, to sort of understand that for when you're looking at determinants and how they relate to entropy and the coverage of the Gaussian. It's giving you the number of things this Gaussian thinks are possible. If it's large, it's covering a large area. Yeah? Now, what we're at the square thing, when you sort of see that, I've done a little sneaky trick because it's not the product of the, well, if you go back here, it's clear it is the square root of each of these. It's sigma 1 times sigma 2. Yeah? But if you think about this basis, sigma 1 could be minus sigma 1. It's a standard deviation. It gets squared anyway. That gets lost. So if you don't do the square and square root operation, you can have a negative answer. So when you see this determinant at the end, it's not the determinant of the real thing. It's not actually the product of these guys. It's the product of these guys squared. So it sort of loses the sense of the volume, apart from when you realize at the end it's all just square rooted again. And that's just an operation that ensures it's positive. If you took the determinant of the basis itself, there's no guarantee that this basis would lead to a positive volume. So you need to square and square root it, and that's what the square root is. So this is the determinant of the basis squared. Yeah? And then it's square rooted. So giving you the volume of what this Gaussian is sitting on. Very precisely, that term is representing, if you multiply all your standard deviations together, the axis aligned standard deviations, then that's giving you the volume of the distribution. So it's giving you a capacity measure. Okay. So I'm going to leave it there, but next time we'll start by doing that. Bayesian fits to that data. So this is like sustaining the uncertainty, and the magical thing will be is even with 4th order on the validation set, we get good performance. Versus, remember before, it was rubbish by this time, wasn't it? But here we're considering all possible. Look at where the line goes. Before, remember how it flipped up and down and all that sort of stuff? Here, once we sustain the uncertainty, the mean prediction starts flowing through the data. But it says, and I have no idea what else is going on. You've given me these polynomial bases. They could do anything outside the regime of the data. Validation set, training set. So, and that's what the model says. It says, up to here, pretty confident about what's going on in your data. Some uncertainty because of crazy runs that took place a while ago, but pretty confident about where things will be. In the future, no idea, mate. Could be anything. I think you'll all agree that's probably, and that's a 5th order polynomial. It hasn't overfit. That variance problem has disappeared. All through the wonderful world of Bayesian inference. The 6th order one does slightly worse because it starts collapsing down. But look at that sustained uncertainty. This error is based on the mean prediction only. It doesn't even take into the account that our model is shouting, I have no idea what is going on, please do not trust me. And that's what you want in an automated system. If you don't want human intervention all the time, you want your model to be constantly saying stuff like that. And that's where Bayesian inference will get us. But we'll look at that next time. Okay? Because we've already overrun. Any questions?
I need to rightly understand the idea of Gaussian noise. For lack of a better word, is Gaussian noise trained or educated noise?
What do you mean by trained or educated noise?
The way you would like to preset the noise for your model.
Well, Gaussian noise has certain characteristics. It's true that you can show various things about it, that like it won't have extraordinary output values like this. If that was the mean, that is very unlikely under a Gaussian distribution. If you look at the probability, as you move 5 standard deviations away from the mean, which that probably is, you'll see it's never going to happen in the lifetime of the model. So Gaussian noise doesn't believe in extraordinary happenings. There's an amazing distribution called a Cauchy distribution, which is infinite variance. And you think, well, how can you have infinite variance distributions? And there's a lovely example, I think due to Steve Gull, which is online, about how this distribution can exist. So imagine we have an infinite coast. Okay, we're already in some quite strange land. So we've got a sea and we've got a lighthouse. And the lighthouse is an unusual lighthouse. It spins, it shines a light, but the light flashes on and off in a uniformly random way. Yeah? So it hits the land. You can only measure where the light hits the land. Now you might think, if you wanted to estimate where this lighthouse was, you could just average the locations where the light has hit the land. But this distribution is very non-Gaussian. So if the lighthouse fires at 89.5 degrees, it ends up a long way down the coast. So it ends up a long, long way away. If it fires at 89.9 degrees, it ends up even further down the coast, until basically it can fire at 89.99999 degrees. That can happen. And the thing's sort of going off towards infinity. So there is a true distribution. There must be a true distribution of where these samples land. But the amazing thing about this distribution, so normally with a distribution, if you want to compute the mean of the distribution, you integrate that, yeah? What happens if that integral doesn't exist? It's still a distribution, p of x dx. That exists. But as soon as you put an x in front of it, these tails of this distribution go to infinity, so it's slower than x, well, 1 over x. So once you've, faster than 1 over x, faster than 1, no, slower than 1 over x. So once you've multiplied by x, it's non-normalizable. The mean of the distribution doesn't exist. And this setup is that example. Just a constant rate spin and uniform firing of the lighthouse. Trying to work out where the lighthouse is by adding up these numbers and taking the mean of these numbers. And you'll never get an answer. You just might get an answer around here, and just as you're thinking, oh, the answer's converging, the lighthouse will fire close to infinity, and your mean will jump out. This integral never converges, so that mean will never converge. Now, that's a very, very heavy tail distribution. But there are other distributions, so where x squared doesn't exist. So if you try and compute the variance, that's non-finite. And the condition for the central limit theorem is that that must exist in the distribution you're using. If it doesn't exist, then the central limit theorem doesn't work, and you will have heavy-tailed things going on. So mathematically, I mean, in practice, you may not even have enough sums in your noise to get towards a Gaussian. So these things can occur, and they do occur in practice. And that example is one of them, where the organization of the Olympics was crazy, and so that basically there's a large perturbation. Or if we decided to do something really stupid like hold a World Cup in Qatar, you know, in the middle of the summer, and it would be super hot, then probably all the results would be a bit crazy. And again, you would get a very strong noise. It's because the influence on the event of that one thing is not the sum of many things. So you don't get a Gaussian result because it's all dominated by the heat or dominated by the dust. You need to include that in your model. Or you need to have a noise model that accepts you haven't included crazy things in your model. Vital in economic forecasting. So the world financial crisis was caused by people not using heavy-tailed noise models, by using Gaussian noise models and having assumptions about independence which were flawed. So things like Russian debt defaults are enormous big jump, just like the sand in the air in the marathon. And they cause noise, which is very heavy-tailed. It's like this distribution, not quite like that distribution, but perhaps doesn't have a finite variance. But they're analytically much harder to deal with, so people tend to avoid them for computational reasons. So yeah, I mean, we're going to do everything with Gaussian noise because it keeps things simple, but you're absolutely right that there can be all sorts of non-Gaussian things going on, and the failure to model them causes enormous problems because you can't regularize it out again. You can't, basically, these effects. What it means is, even in this zone here, a result up here would be quite likely. But under a Gaussian distribution, that result is so unlikely as it would never happen. Because if you think about its probability, it's governed by, okay, so, well, the Gaussian distribution has the property that all moments exist because the tails go down exponentially quadratically. So all these moments, you can put x to the 6 exist. Every single one exists. So it's quite a conservative distribution. It thinks things come around the mean more. Now, if I say something's 5 standard deviations away from the mean, then what the effect of that is that I have a variance of, I basically end up, so 5 standard deviations away from the mean is that it's 5 times sigma in this thing here, all squared, divided by sigma 2 sigma squared, yeah? So it becomes 25 over 2, e to the minus 25 over 2. So that's really small. It's in the exponential, it's going up quadratically. So the probability, okay, if the standard deviation is 1 on the outside, you then basically get a multiplier of 1 over 2 pi. So that does nothing to fix this. The probability is dropping in this exponentiated quadratic type form, which means that 5 standard deviations of the mean is impossible. If you think of that, you know, when you try and compare it to count probabilities, you have to be a bit careful because obviously this is a probability density. So what we really need to look at is the small region around. You can't talk about the probability of a single point. But if you start looking at the small region around the point or the probability above, you integrate above, you still find that the probability of any point being greater than 5 standard deviations of the mean, which is basically requires you to do this integral here, is minuscule. It's really tiny because the tails are dropping so quickly. So it basically doesn't believe in that point, the model. I mean, it's really affecting the likelihood quite strongly, and that's pulling things too far north in some sense. So Gaussian noise can be a problem. Other questions? Okay, so we'll carry on tomorrow, and we'll do Bayesian. We'll finish the Bayesian modeling and then turn it into Gaussian processes.
So I guess we'll find out